Hi everyone, I'm Lynn Gabud. Welcome to my lecture series on Introduction to Computer Programming. In this video, I'm going to share with you some fundamental concepts in computer programming. What is a computer? What does it do? What's the role of recipe and languages in computer programming? So let's start with computer. So as a user, we know that computer is like this one, a desktop, a laptop, a tablet, or maybe a smartphone. And we buy and use these gadgets to access these applications. For example, we use computers to create our PowerPoint presentations, our Word documents. We access our social media accounts like Facebook, and then we do our shopping online. We order our food online. We also book our deliveries, and we do online banking as well. And of course, we play our games. Um, yeah, there are a lot of things, especially nowadays, there are a lot of things that we do with our computer. And this computer is the hardware. These are the tangible, the things that we hold, we actually see, and these are the software. Software is not limited to this special purpose software, because operating systems such as Windows and Mac OS X are also software, and even compilers and interpreter and the IDEs that we use for programming are also software. So basically everything that runs in a machine are software. That's how we see a computer. And the hardware, the computer hardware has basic parts such as CPU, which serves as its brain. So we have to take note that the machine or the computer has very simple brain. It knows also, it can follow instructions, it can perform calculations that we specify via the program, but that's all it can do. Um, the data instructions are stored in the memory, and this memory are divided into storage locations which have addresses. And the brain or the CPU accesses this memory using these addresses. The computer has two types of memory. The main memory, or the RAM, which is volatile, which this means that if we turn off the computer, the data in the main memory will not be available the next time we turn it on. While the secondary memory is non-volatile. So examples of this are the hard disk and USB drive, memory card, and of course cloud storage such as Google Drive and Dropbox. So the secondary memory, even if we turn off the computer, our data stored in this secondary memory will be available the next time we turn on our computer. We, as user, communicate with a computer through I/O devices. For example, the computer gets information from the user, maybe through the keyboard, and the computer gives message to the user using maybe a screen or a monitor. That's where we see the output of a program. That's how we see the applications or the software running in the computer. So these components form part of computer hardware. And this is how we know a computer. There is hardware, there is software. But then, what is a computer in the eyes of a programmer? So, since we are to be future programmers, let's dig into deeper. Let's dig into it deeper. So, what does a computer do? Fundamentally, computer performs calculations. and it's good at it because it can calculate with high accuracy, and it's fast in calculations. It can remember results. The computer does this, but by storing data in storage in the memory, and the kind of calculations that the computer the computer do it are built into the language, and it can also do calculations that you define as a programmer. But we have to take note that computers only know what you tell them. Okay, so a computer doesn't have, let's say, a mind of its own. It doesn't have the intelligence as we have. So all it does is follow instructions or execute instructions that we give the computer. So the intelligence it forms are from the knowledge that we give the computer. So that's how computer work. That's how computer works. So it won't do anything that we, the programmer, won't give them or won't instruct them. So that's how, let's say, stupid they are. Okay. So, and how do we communicate with them? How do we tell the computer what to do? So let's go back to some definitions of knowledge. Declarative knowledge. These are statements of facts. So for example, a family will have scrambled eggs this morning. This is just a statement of fact. So we are saying that, oops, family will have scrambled eggs this morning. But it's different, a lot different from an imperative knowledge, which is a recipe or a how-to. So here, in this example, steps 1 of 7, this one is a recipe or a how to cook scrambled eggs. So the first step is, let's say, Lynn beats 2 eggs until fully blended. Step 2, Lynn prepares the pan. Then Lynn pours the eggs in the pan. Lynn moves the eggs across the pan until the eggs cook evenly, and then turns the egg onto plate. Lynn serves the scrambled eggs on the table, and the family digs in. So, yeah. So that's a recipe. We all know this because at some point in our lives we've done some sort of cooking. We've seen some recipes, and yeah, this is a step-by-step instruction on how to do something or how to arrive at something. And let's try to look at an example that is a little bit closer to computing. So here, square root of a number x is y, such that y times y is equal to x. So this statement is a declarative knowledge. It tells something, but it does not tell how to do it. It's not a recipe. And a well-known recipe algorithm for getting the square root of a number is this one. Here is an example. So let's say we have 16 as value for x. So we start with a guess g. So here it's g. And then we check or we test if g times g is close enough to x. Here, 9 is the answer. And 9, I don't think it's close enough with to 16. So we do step 3. Otherwise, make a new guess by averaging g and x over g. So here, the average of g and x over g is 4.17, and this becomes the new value for, or the new guess for g. We put the value here. And then repeat the process. We start with step 1 again. So if g times g is close enough to x, this time the value is 17.36. We stop. So I don't think this is already close enough to 16. So we go on. We get the new guess, or the new value for g, which is 4.0035. And then this new value of g, with this new value of g, we go to step 2, and we get the value of g times g is 16.0277, close enough to 16. I do think yes. The answer is yes. So if yes, we stop and we say that G is the answer. Okay. So this part, this steps 1 up to 4, is a recipe, right? This is very similar with the recipe we had with the recipe of the example we had in the previous slide, which is cooking scrambled eggs. So this one also is it's a recipe, and take note, it's a numerical example, which means we can do this how-to in math, with math. Okay. So this recipe, what do they have? So the recipe has simple steps, which you've seen. We had step 1, 2, 3, up to 4. There is a control. There is a flow of control. So if you noticed, at some point there's a step that that we made decisions. So we decided whether the new value of g is close enough to what we want. All right. So, and then there was also a step, or at some point there were steps that we repeated. So then we continuously do some steps until we decide that it's close enough to, that g times g is close enough to the value to the x that we are looking to the given value of x. And then there is also a way to stop. So when did we stop? When we thought we decided that the value are close enough. So these are the important components of a recipe. Simple steps, flow of control, and a way to stop. This is an algorithm. Okay, so recipe is an algorithm. That's why it plays a special role, a very important role in programming. So a recipe has ingredients. What are these ingredients? In cooking, this maybe eggs, oil, and so on. But in programming, in computer programming, these ingredients are the data that that the program processes. So this data may be a real number, maybe numbers, maybe characters, maybe text or words. So data comes in many types. That's why computer stores them in different ways. Recipe also has operations. In cooking, it's like fry, slice, beat, turn. But in computer programming, these are operations. These may be operations such as addition, subtraction, multiplication, and division. So computer, since we are dealing with computers, we want to capture this recipe in a mechanical process, because computer is a machine. Historically, there were fixed program computer, or I would say that computers started as fixed program computers, and an example of it is a calculator. Fixed program computer, like a calculator, can only do addition, subtraction, multiplication, division. We cannot use it to plot numbers. We cannot use it. We cannot add features to it, or we cannot add software to it. So, fixed program computer, if you want the machine, the computer, to do something else, or you want to add to it, you have to create another machine that does another thing. So, yeah, because people wanted to do more with a machine, with a single machine, the store program computer came in. So these are the machines that store and execute instructions. They can stored program computers can execute different instructions. You can add instructions to it. So these are what we know as computers nowadays. So we add applications, we add programs. So this is the computer now. This is the computer we know right now. So a computer has this basic parts, or this is the basic architecture of computer. It has memory. The memory contains data and instructions. The ALU, or arithmetic logic unit, this part does the instructions. So it executes the instructions using primitive operations such as plus, minus. And then the control unit has one program counter. And what this does is the control unit handles the sequence of execution, the sequence of instructions. So for example, let's say this a program starts. So what happens is the control unit, it gets the first instruction in the sequence. Let's say this is the sequence of instructions. It gets the first instruction. This first instruction goes to the control unit, and then the control unit interacts with the ALU. The ALU determines what kind of operations are needed for these instructions. At some point, it may get data from the memory. After it gets data from the memory, it executes the instruction, and then it may return data to the memory as well. So after processing that instruction, it goes to the control goes to the control unit, and then the program counter increments. So it goes to the second instruction in the sequence, and then the same process. The ALU processes or executes the instruction, and then the control unit goes to the next instruction. At some point in this series of instructions or sequence of instructions, a test may be done. So there may be a test such as is equal to or is greater than. And then depending on the answer to that test, whether it's true or false, control unit may go to the next instruction in the sequence, or it may go back to a previous instruction. It may do the previous instruction and do this again, this 1, 2, 3, 4. So there you will notice that even at this level, there is a flow of control, and the control unit handles that. Okay, so that's how the computer, the machine works at the low level. So this is the basic architecture of the computer. The stored program computer contains sequences of instructions. The primitives operations it can do are addition, subtraction, and logic. It can do some tests, simple tests, such as is something equal to or something greater than. It can move data, like store data, and special programs such as interpreter, and such as an interpreter, for example, Python interpreter, controls how these instructions are executed. So it controls the flow of these instructions. It decides which instruction to execute. It decides which instructions should be repeated, and it decides when it should stop. So that's what the interpreter does. And Alan Turing, a very great computer scientist, showed that we can compute anything using just 6 primitives. The 6 primitives are move left, move right, read, write, erase, and hop. So imagine that just with these 6 primitives, and he proved that we can program anything. And because of this 6 primitives, or through these 6 primitives, modern programming languages, or the programming languages now were created, so which have more or easier to use primitives. So you can just imagine that you, as a future programmer, you can also, or you will be able to create new primitives as well. So that's how programming developed. So everything came about from this just 6 primitives. And theoretically, it is believed that anything computable in one language is computable in any programming language. It means anything you program in Python, you can also compute, or you can also do in C or any other language. If you want to create a program in Python, well, what if we do, or we program using just these 6 primitives? So that's how wonderful programming is. So everything was just built on top of the other. And yeah, languages provide a set of primitive operations, and these primitive operations are combined so that we can create expressions, and expressions evaluate to values, and these values have their meanings in a programming language. That's how the recipe or the algorithm works. Let's now go to languages. Let's focus on the aspects of languages, and let's compare or look at it in parallel with the English language. So the English language has this primitive constructs, such as these words. So English has words, while programming languages have this float, boolean, int, plus, minus, or multiplication, and so on. So these are the primitive constructs. In English, we can create phrases. In programming languages, we can create expressions from primitives. So, for example, in English, we say or we write down cat, dog, boy. This is not syntactically valid. So noun is not syntactically valid, while in the second example, cat hugs boy is syntactically valid. So it's noun, verb, noun. In programming language, this string hi followed by a number 5 is not syntactically valid, while this 3.2 times 5 is syntactically valid. So this one is operand, operator, operand. So both the English and the programming language follow some form of syntax. And then this some phrases in English may be syntactically valid but are static semantically invalid. For example, I are hungry. It's noun, verb, adjective, but then it doesn't make sense, right? So it has a static semantic error. While in programming language, in this example, 3.2 times 5 is syntactically valid, while 3 plus the text or the string hi evaluates or results to a static semantic error. In English, some sentences or phrases can have many meanings. For example, flying planes can be dangerous. It could mean that the act of flying planes is dangerous, or the plane that is flying is dangerous. Do you get what I mean? While in programming languages, an expression can only have one meaning. But the problem is sometimes that's not what the programmer intends to do. Okay? So it will never have another meaning. For example, if for some reason the x is assigned a value of 10, it's not because of magic. It happened because at some point the programmer instructed the machine to assign the value 10 to x. So there's no magic in programming. And if you write a code, it will just have one meaning. Okay? So do not say that, oops, what's happening? It's getting weird. No. Something is wrong with your recipe or with your solution. Okay? Because a statement or an expression will not have two meanings. So where things go wrong, where are the errors? We have syntactic errors. These are common and easily caught. We can see it when we run the program or we compile it, if it's a compiled program. Static semantic errors, some languages check this, all right? But some, they don't have it, okay? So, but then it's something that we can trace, we can look into. But then the difficult part or the problem that most programmers encounter is that what's happening is different from what the programmer is imagining. What's in the mind of the programmer does not connect or is disconnected from what the computer is doing. So that's the time you have to think about your solution. You have to look for the problem or the error. And that's a problem that is very difficult to solve. All right. So we really have to be careful, and this is the skill that we have to develop, creating programs that is clearly the solution in our mind. Okay, so this problem may produce crashes, program crash or stop. It can loop forever, and it may give answers which is different from what we expected. So to wrap it up, we talk to other people using human language, for example, English. We talk to a kid using maybe kid or baby language, right? Still in English, but then with some variations so that the kid would understand. And our dogs loves us because we communicate with a dog in the language that both of you understand. And here in programming, we communicate with a computer using programming language. All right? So that's what we are going to learn. So our class is on Introduction to Computer Programming. We are going to use Python as a language. And our aim is to learn how to talk to a computer, to learn how to give them instructions. Why is it difficult? Because computer is not intelligent. Because computer is so dumb and stupid. Right. So that's all for today. And if you have questions, you may email me, or you may send or post your questions on our group discussions. And that's all. Have a great day.